Hey guys, it's JJ from Radiotech Academy. And as promised, I'm back with part 2 of our radiation and DNA series. In the last video, we talked about how radiation damages DNA and how cells try to repair it. But today we're going deeper, exploring cellular responses and what really happens when DNA takes a direct hit from radiation. So stick around till the end. This one's going to be fascinating. LET and radiation type. All right, everyone. Now we're diving into something called LET, or linear energy transfer. Sounds fancy, but it's basically a way to measure how much energy radiation dumps into cells as it passes through. Think of it like this. LET tells us whether the energy is packed in one spot or spread out over a bigger area. And that makes a huge difference for DNA damage. High LET radiation. High LET radiation includes alpha particles, neutrons, and heavy ions. These guys are big, slow-moving particles that release a ton of energy in a very short distance. The damage is dense and clustered, lots of lesions packed close together. Your cell's repair systems, even the super-accurate ones like homologous recombination, can struggle to fix this. Result? Mutations, chromosomal breaks, or cell death. Analogy: imagine dropping a heavy iron ball on a wooden floor. It makes a deep dent in one spot. That's what IELET radiation does to DNA. Low LET radiation. Low LET radiation includes X-rays, gamma rays, and beta particles. These are light, fast particles that release energy slowly over a longer distance. The damage is scattered, isolated breaks, or small chemical changes. Cells can usually repair this damage more easily using systems like base excision repair (BR) or nucleotide excision repair (NER). Analogy: imagine dropping a small rubber ball repeatedly across a floor. Many small dents appear in different spots. That's low LET radiation in action. Biological consequences: high LET. Harder to repair, more lethal or mutagenic. Low LEs, easier to repair, less lethal. Cells have a better chance to survive. In radiotherapy, doctors sometimes use high LET radiation to target tumors that resist normal X-rays. LET also influences how well repair systems work and how accurate they are. And here's a quick summary table to make it clearer. High LET radiation. This one includes particles like alpha particles and neutrons. They carry a lot of energy and release it over a very short distance. The DNA damage they cause is dense and clustered, often leading to double-strand breaks. Because of that, cells find it really hard to repair. Biologically, the effects are usually severe, sometimes mutagenic or even lethal. You can think of it like a heavy hammer hitting one spot on the floor. It leaves a deep dent right there. Low LET radiation. Now this includes X-rays and gamma rays. They carry lighter energy that spreads out over a longer distance. The DNA damage here is scattered, mostly single-strand breaks, which cells can repair much more easily. Its biological effect is milder, so cells have a better chance of survival. You can picture it like a gentle rain of tiny pebbles falling across a wide surface. Small hits, but nothing too destructive. Analogy recap: high LET radiation is like a heavy hammer hitting a single spot, leaving a deep dent. Low LET radiation is like a light rain of tiny pebbles, leaving small marks over a wide area. This is a great way to visualize how energy deposition affects DNA damage. One is concentrated and destructive. The other is spread out and easier to handle. Cellular and tissue responses. Now that we understand how DNA gets damaged and the repair pathways, it's important to see what happens at the cell and tissue level. Cells aren't isolated. They exist in tissues and organs. How they respond to damage can affect tissue function and overall health. 1. DMA damage sensing. Cells have special sensors that detect DNA damage. Proteins like ATM and ATR act like security guards. They notice broken strands or chemical changes in DNA. Once damage is detected, these sensors activate signaling proteins like p53, CHK1, and CHK2, which guide the cell on what to do next. 2p53, the guardian of the genome. p53, is a key protein that decides the cell's fate. If damage is minor, p53 pauses the cell cycle, giving the cell time to repair DNA before dividing. If damage is severe, p53 can trigger apoptosis, a controlled self-destruction that protects surrounding healthy cells. p53 can also trigger senescence, where the cell stops dividing but remains metabolically active and can influence neighboring cells through signaling. Cellular outcomes. After detecting DNA damage, a cell can follow different pathways. Successful repair, DNA is fixed, and the cell continues normal function. Senescence. The cell stops dividing permanently but stays alive, preventing mutation spread. Apoptosis. Controlled self-destruction to protect tissue. Necrosis. Extreme damage can cause uncontrolled death, releasing contents and triggering inflammation. Tissue sensitivity. Different tissues respond differently, often depending on how fast their cells divide. Rapidly dividing cells, bone marrow, intestinal lining, skin are more sensitive. Slowly dividing or non-dividing cells like neurons are less sensitive, but may show delayed effects. Acute versus late effects. Acute effects appear within days or weeks. For example, skin redness, inflammation, diarrhea, low blood, cell counts. Late effects appear months or years later. For example, fibrosis, scarring, reduced organ function, infertility, chronic tissue degeneration. Summary of key points. Cells detect DNA damage and activate repair or protective pathways. p53 acts as the guardian, pausing division, triggering repair, or initiating apoptosis. Tissue sensitivity depends on cell division rate and maturity. DNA damage effects can be immediate or delayed, affecting tissues and overall organism health. Analogy: imagine a factory producing products. Each worker is a cell. If a worker makes a mistake, DNA damage, the factory manager, p53, can pause the line, fix the problem, or remove the worker. Some departments, tissues, have fast workers who make more mistakes, while others work slowly and tolerate minor errors better. DNA damage signaling pathways and the role of p53. When DNA gets damaged, cells don't just ignore it. They immediately activate a series of signaling pathways to decide what to do next. This is extremely important because even a single damaged DNA molecule can affect the entire cell. If left unchecked, this damage can lead to diseases like cancer. DNA damage sensor cells have specialized proteins called sensors that detect damage in DNA. Two of the most critical sensors are ATM and ATR. ATM, ataxia telangiectasia mutated, detects double-strand breaks, the most dangerous type of DNA damage. ATR, ATM, and RAD, 3-RAELATE, mainly responds to single-strand damage and problems during DNA replication. Once these sensors detect a problem, they send signals to other proteins, activating a cascade of responses. Key signal proteins include p53, CHK1, and CHK2. These proteins communicate whether the DNA can be repaired, whether the cell should pause division, or whether it must self-destruct to protect the organism. p53, the guardian of the genome. p53 is often called the guardian of the genome because it decides how the cell responds to DNA damage. Its main functions include cell cycle arrest. If the damage is minor, p53 pauses the cell cycle. Think of it like stopping the production line in a factory to fix a small mistake before it becomes a bigger problem. Apoptosis programs cell death. If the damage is too severe, p53 triggers apoptosis, This is a controlled self-destruction mechanism that prevents damaged cells from spreading mutations. Senescence p53 can put the cell into a state called senescence, where it stops dividing but stays alive. These cells continue metabolism and can send signals to neighboring cells, preventing the propagation of errors. Analogy for easier understanding. Think of a cell as a factory, and DNA as the instruction manual for producing products. ATM and ATR, quality control inspectors checking the instruction manual for mistakes. The factory manager is P53. If a small error is found, the manager pauses the production line to fix it. Cell cycle arrest. If the damage is too big, the manager shuts down the line completely. Apoptosis. If the line can't operate normally but isn't dangerous, the manager keeps it idle for maintenance. Senescence. This system ensures that only high-quality, safe products, proteins, and cellular functions are made, and errors don't spread to new cells. Why this matters? Without P53 and these DNA damage signaling pathways, cells would divide with broken DNA. This can lead to mutations, permanent errors in the DNA sequence, genomic instability, misaligned or lost chromosomes, uncontrolled cell growth due to faulty regulation. Key takeaways: DNA damage sensors detect problems and activate signaling cascades. P53 decides whether to repair, pause, or eliminate the damaged cell. The balance between repair, apoptosis, and senescence protects tissues and the organism. Failure in this system can lead to mutations, cancer, and aging-related issues. Summary: DNA damage sensors detect errors. P53 decides whether to repair or eliminate cells, and senescence, apoptosis, or repair pathways protect the organism from mutations, cancer, and tissue degeneration. Apoptosis versus necrosis. When a cell is damaged beyond repair, it has two main paths it can follow: apoptosis or necrosis. These are two very different ways in which a cell can die, and understanding the difference between them helps us see how the body protects itself from damage. Let's start with apoptosis. Apoptosis means programmed cell death. It's like the cell decides to take itself out of service in a calm, controlled way to protect the body. You can think of it as a cell committing a peaceful, organized suicide. During apoptosis, several things happen inside the cell. The cell becomes smaller. Its nucleus, the part that contains DNA, condenses. The DNA itself breaks into neat, small fragments. The cell's outer membrane stays intact, so the inside materials don't leak out. Because of this, apoptosis doesn't harm the neighboring cells. There's no inflammation, no swelling, and no chaos. It's almost like the cell quietly turns off the lights and locks the door before leaving, calm, clean, and efficient. Now let's look at necrosis. Necrosis happens when the damage is sudden and severe, like what might happen from a burn, lack of oxygen, or high-dose radiation. In this case, the cell loses control of its internal systems. The cell swells up, its membrane bursts, and its contents spill out into the surrounding area. This causes inflammation, pain, and often damages nearby healthy cells as well. It's a very messy process, the opposite of apoptosis. If we use a simple analogy, apoptosis is like slowly turning off a light switch when you're done with it. Necrosis is like a light bulb exploding, sudden, chaotic, and dangerous to everything nearby. So, in summary, apoptosis is controlled, organized, and protective. Necrosis is uncontrolled, destructive, and inflammatory. Both are forms of cell death, but apoptosis keeps the tissue healthy, while necrosis can lead to more damage and even tissue destruction. Tissue sensitivity. Let's summarize how different tissues in the body respond to radiation based on their proliferation rate and biological sensitivity. Bone marrow has a very high rate of cell division because it constantly produces new blood cells. That's why it's one of the most radiation-sensitive tissues in the entire body. When radiation damages bone marrow, it reduces the production of red blood cells, white blood cells, and platelets. This can cause anemia, weak immune response, and bleeding problems. Intestine. The intestinal lining renews itself all the time, so it also shows a high level of sensitivity. Radiation can disrupt this process, leading to inflammation, diarrhea, and poor nutrient absorption. This is why the digestive tract is one of the key organs affected during radiation therapy. Skin. The skin's outer layer, called the epidermis, has a moderate level of cell turnover. Therefore, its sensitivity to radiation is also moderate. Common effects include redness, swelling, and temporary hair loss. Most of these reactions are temporary, as the skin can usually repair itself over time. Gonads, testes, and ovaries. Reproductive tissues have a high rate of cell division because they constantly produce gametes. That makes them very sensitive to radiation exposure. The result can be temporary or even permanent infertility, depending on the radiation dose and exposure duration. Brain and adult nervous tissue. The brain and other mature nerve tissues have very low cell division activity. That's why they are among the most radiation-resistant tissues. However, after high or long-term exposure, delayed effects like inflammation or neurodegeneration can still occur. In short, rapidly dividing tissues such as bone marrow, intestine, and gonads are the most sensitive. Slowly dividing or mature tissues such as the brain and nervous system are much more resistant to radiation damage. Summary table of tissue sensitivity. Bone marrow has a very high proliferation rate and is extremely sensitive to radiation. Exposure can cause anemia and a decrease in white blood cells and platelets. Intestinal tissue divides at a medium rate and is highly sensitive. Radiation may cause inflammation of the intestinal lining, leading to diarrhea or discomfort. Skin cells also have a moderate division rate and medium sensitivity. Common effects include redness, irritation, or mild inflammation, also known as radiodermatitis. Gonads, such as the ovaries and testes, show high proliferation and high sensitivity. Radiant exposure can lead to temporary or permanent infertility, depending on the dose. Brain and adult nervous tissue have a low division rate and are mostly resistant to radiation damage. E cells rarely divide, so they show minimal direct effects, though secondary or delayed damage can occur with very high doses. Timing effects when radiation shows its impact. Let's talk about timing effects, how radio affects the body at different times after exposure. We usually divide these effects into two main categories: acute effects and late effects. Acute effects, these appear within days or weeks after radiation exposure. They happen because rapidly dividing cells are hit first. Typical examples include skin redness and inflammation, diarrhea due to intestinal cell damage, a rapid decrease in blood cells, radiodermatitis, skin irritation and peeling. These effects are often temporary, but can be intense, depending on the radiation dose and tissue sensitivity. Late effects. Late effects develop slowly, sometimes months or even years after the exposure. They occur because surviving cells and tissues gradually lose function or structure. Examples include tissue fibrosis, normal tissue becomes stiff and scar-like, reduced gonadal function, leading to infertility, chromosomal instability in surviving cells, increasing long-term cancer risk. Acute effects equals early, short-term reactions. Late effects equals delayed, long-term consequences. Tissue sensitivity, dose and radiation type influence, timing and severity. In simple terms, acute effects happen soon and are usually temporary, while late effects show up much later and are often permanent. Overall video summary. Alright everyone, let's take a step back and see the big picture. When radiation enters the body, 1. Water interaction. Radiation first collides with water molecules, producing free radicals, highly reactive particles that attack biomolecules. 2. DNA damage. These radicals, along with direct radiation, can break DNA bonds or modify DNA bases. 3. Oxygen enhancement. Oxygen can make this damage worse by stabilizing radicals. This is called the oxygen enhancement ratio, OER. Types of DNA damage: base modifications, small chemical changes in A, T, C, or G, single strand breaks SSB, one DNA strand is cut, double strand breaks DSB, both strands break. The most dangerous, cross-links or oxidation, can make repair even harder. DNA repair pathways. Base excision repair fixes small base changes. Nucleotide excision repair, rupture or bulkier surface damage. DSB repair, non-homologous end, joining fast but error-prone. Homologous recombination, slower but highly accurate. If repair fails, outcomes can include mutations, uncontrolled cell division, cancer, apoptosis, programmed cell death. Role of LET, linear energy transfer, ILET, radiation, alpha particles, dense, clustered DNA damage, hard to repair, more lethal, low LET, radiation, gamma rays, X-rays, scattered, easier to repair damage, cellular responses, successful repair, cell lives normally, senescence, stealth dividing but stays alive, apoptosis or necrosis, cell dies, sometimes releasing contents that affect tissues. Tissue sensitivity depends on cell division rate and maturity. Rapidly dividing tissues, bone marrow, intestines, gonads, highly sensitive, mature non-dividing tissues, brain, neurons, more resistant. This is summarized by the law of Bergoni and Tribando. Clinical radiation effects. Acute effects, days or weeks. For example, anemia, skin inflammation, diarrhea. Late effects, months or years. For example, fibrosis, infertility, degenerative tissue changes. Key takeaways: cells may experience successful repair, senescence, apoptosis, or necrosis. P53 acts as the guardian of the genome, deciding between repair and programmed cell death. Tissue sensitivity depends on proliferation rate and cell maturity. Radiation effects can be acute or delayed, each with unique outcomes. All right, everyone, that's it for today's session. Thanks so much for staying with me till the end. I really appreciate it. In the next episode, we'll probably talk about dose effects, risk management, and dose-response models. So stay tuned for that. If you enjoyed this video, please give it a like, leave a comment to share your thoughts, and tell me what topics you'd like to see next. And if you found it helpful, share it with your friends. It really helps the channel grow. If you haven't subscribed yet, make sure to subscribe because it truly gives me the energy to keep creating new content for you. Thanks again, take care, and I'll see you in the next video.